Welcome. Differentiability. Well, we have seen the definition of derivative. We've even solved an example using derivative, the concept of derivative in the definition of derivative to find a slope of a tangent. So not all the functions, not all the equations of a slope, they're going to represent something that can be differentiated at a given point or at a given interval. There are some criteria that we have to see to check whether the function is differentiable at that point or not. And this thing of checking whether the function can be differentiated or not, it's under the term differentiability, the ability to be differentiated or not. So these are the three indicators we have to know whether our function can be differentiated or not. So number one, the first indicator we have is a sharp point on the graph. Sharp point on the graph. What it means basically is that whenever you have a function in which it suddenly changes its behavior at a given point, that function is not differentiable. So how does it happen? Imagine that this is a graph f of x, and this graph was moving in this direction, and then suddenly it changed, like suddenly, so abrupt. And as we know that the definition of derivative is the rate of change of something by another thing, delta x by delta y. Thus far the tangent was something like this, and then it became like this, and then it came to a point that the tangent was something like g, but suddenly this g turned to be in the other side. So this is not t, but this is also g. After, you can call us g dash. So this g dash is how the tangent will look like from the moment it crosses to this point, that we can call this point as point A. So from point A we have a sharp change, and we have this small angle which you can call a theta. So all the concept we have of derivative as the rate of change does not work in this point, because it was changing gradually and gradually and gradually, but there's no gradual over here. It's sudden. If it was a movement of a car or a vehicle, it wouldn't be a smooth transition, because there was no inertia obeyed over here. It's suddenly changing, which cannot happen. So whenever you have a graph or a graph that represents a function in which at a point this situation arises, in which if you draw a tangent it suddenly changes its orientation at a given point, because you said sudden means there is no rate of change, it didn't change gradually, meaning that at that point you cannot apply the concept of derivative that you know. This is the first case. So a sharp point on the edge means not differentiable. Then we have the second thing. So another condition says the tangent is parallel to the y-axis. We are here. Imagine that you have a graph of a function f of x. It's along y and x axis, and I think we already know that f of x is the same thing as y. So this function, as you can see, it has this behavior. It's moving to in that fashion. If you draw a tangent, in the beginning the tangent will be something like this, and then it becomes something like this. Of course it's touchy, and then when it reaches to some point here, the tangent will be in a 90 degrees with relation to x. So we have 90 degrees that is made by t, which is the tangent, and the x-axis. And because you have this thing, you cannot use the concept of derivative. Why? Because at this given point, first of all, limit does not exist. Why limit does not exist? Because this limit will tend to infinity, because the tangent of 90 degrees, you check on a calculator, it's going to give you math error, because you are going to some infinity. So at this given point, whenever the tangent is parallel to the y-axis, which is perpendicular to the x-axis, at that given point at which that kind of situation arises, our tangent is 90, and the limit, it does not exist. So this again is a situation of not possible to find derivative of a function at that given point. This point we can call as b in this function. So the third point is existence of a limit. So the third point is existence of a limit. We have two graphs. The graph of a function f of x is equal to x squared plus 3, and the graph of the function 1 by x. So this is a quadratic equation, and this not. There's something very curious about this. To check whether the function can be differentiated at a given point or not, we should first make sure that the limit of that function at that given point or at that given interval exists. So to check whether the limit of a function exists or not, there are some tests that we do. So for a limit of a function to exist means that the limit of that function when we tend to that given value either from the left or from the right is going to be the same. So take for example this function, and we can consider a point, say this point. This is the point A, and this point A we can call it as a point where x is equal to 2. So at this given point this function has some value which till now we don't know. This is A. So a limit of a function at a given point exists if the lateral limits of that function at that given point exist and they are the same. So let us see how we solve this thing. So we have our point in consideration, which is x is equal to 2. How do we do this? We have limit of f of x when x tends to 2. That's what we're trying to solve. But this thing is going to be done from the negative side, and limit of f of x when x tends to 2 from the positive side. If these two conditions, if this condition is matched, is satisfied, then our limit exists. So these two limits, whether this one or this one, they are both called lateral limits because they are the sides. So if you see from the graph, we are coming to 2, we are approaching 2 from this direction, and we are also approaching 2 from this direction. So what is the point of a function? What do we see? As we come in first, it was from this point till here, it came, and then we get closer and closer to 2, it was here, closer it's here, and closer it's here, it's tending to this point. And if you do it from the other side, coming closer, you have this, and then you approach, you have this, you approach, you have this. Again, you are coming very close to the same point, this point. So as you can see, either from the left or from the right, we are going to have function tending to a one specific point. So let us prove mathematically. So we have limit when x tends to 2 negative. Well, this function here doesn't have any issue if we do direct replacement. So what we do, we just replace wherever we have x by 2. This thing is not a minus, it's just indicating the side from where we're coming from. So we have 2 squared plus 3. This is 4 plus 3, which is 7. And even if we do limit now coming from the right side, 2 plus x squared plus 3, we are going to have the same thing, we're just replacing. So we have again 2 squared plus 3, which is equal to 7. And hence this function obeys this condition. The lateral limits are the same, but it's not the same when you talk about a function such as f of x is equal to 1 by x. Look at this. So consider that the point that we want to come across is this one, and this point, as we can conclude, this point is 7. This point is 7. So look at this. Well, this function from this side and from this side, we have 2. We approach 0 from the left side. This function is decreasing and decreasing and decreasing. And if we approach 0 from this side, this function is increasing and increasing and increasing. So if we had to do that, imagine that we have a point here, we have a point here, we have a point here, and we also have a point here, here, and here. All these points are getting closer and closer to 0. So from this point we have this value of the function, from this point we have this value of the function, and from this point you have this value of the function, meaning that even if we get closer and closer and closer, we're actually not reaching 0, but we're getting very huge numbers of the graph in the y-axis. So this is all tending to infinity, but because the negative side is minus infinity. And if you come from this side, from this point we have this value of the function, from this point we have this value of the function, and so on. Like, it's growing, it's really growing. So when we reach a point so close to 0, this function is huge in terms of number, So because it's positive, it becomes plus infinity. So as we can see, the limit when this function, when approaching 0 from the left, is different from the limit when approaching 0 from the right. Here we're having positive infinity, and here we're having negative infinity. So mathematically, what we have is limit when x tends to 0 of 1 by x, because our f of x is 1 by x. So as we do that, if we replace, we cannot do direct replacement here and then expect that we're going to have this thing, because we're talking about limit. It's not like we're replacing here by 0. We are taking a number so close to 0, our number so close to 0, to replace here in the place of x. So what we're going to have in the end, if this is negative coming from this side, we are going to have 1 divided by 0 from the left, and this gives us minus infinity. If you put in a calculator, it's going to tell you math error or something like that. And if you come from the right side, limit when x tends to 0 of 1 upon x, this from the right side is equal to 1 divided by 0 plus. We are coming very close to 0, something like 0.0000. The maximum zeros you can put in a calculator, and then you make 1 divided by them, you're going to have a huge number, and this number now is going to be a positive infinity. So the limit when x tends to 0 from the left of this function f of x is not equal to the limit when this same function tends to 0 from the right, and hence the lateral limits are different. If the lateral limits are different, the limit does not exist. So the limit exists only when the lateral limits exist and they're equal. Lateral limits here exist and they are equal. Lateral limits here, they exist, yes, minus infinity and plus infinity, but they are different. Hence the limit does not exist. Because the limit does not exist, we cannot differentiate this function at that point. There's a discontinuity at that point. It cannot be differentiated. And it's very good when we always take the concept of derivatives as a rate of change, because if you try to apply it in a direct real life perspective, what you'll see is that from this point you cannot jump suddenly to the other point with exactly the opposite behavior. So there's no transition, there is no smooth transition, there's no incremental change, there's no rate of change. And if there's no rate of change visually seen in a graph, there is no derivative of that function at that given point. So resuming, a function can be differentiated if the limit exists, yes, but if it has a sharp point on the graph, it cannot be differentiated. If the tangent line is parallel to the y-axis, it cannot be differentiated. The behavior of this graph is equal to the behavior of the graph when we talked about the tangent being perpendicular to the x-axis, because if you have to draw a tangent to this graph, whether taken from the left or right, you are going to have a line which is parallel to the y-axis. And we are repeating what was said when we're talking about the tangent perpendicular to the x-axis and parallel to the y-axis.